All right, so this video we're going to look at the disc method and washer method. I want to explain the disc method and explain the washer method and talk a little bit about how they're related before I get into working the problems. I think if you understand what's going on, it makes the problems a lot easier to set up. All right, so first let's just take a look. Let's look at the disc method. All right, so basically what we've got here is we've got a function, okay? Just some function. Let's just call this function big R of x. You could call it f of x, g of x, whatever you wanted to call it. It doesn't matter. And let's say that we're going to rotate this about the x-axis. So we're going to rotate this thing about this graph here. We're going to rotate it about the x-axis, and we're going to find the volume of the solid that it generates. So if I rotate this down here, all right, so I mean this is supposed to look exactly like this. I know it doesn't, but it's close enough. All right. So what we're going to do with the disc method is we're going to take these discs. Here's a disc, and we're going to find the volume of this disc, and we're going to sum the volumes from whatever this value is to this value, okay? And that will give us the volume of this solid that's generated by revolving this graph about the axis. And in this case, you can see it's the x-axis that we're revolving it about. The same thing applies if we're revolving it about the y-axis. And I'll explain that more when we get into the examples and we start working the problems. All right, so let's look at this just a little bit. So if I'm standing over here, okay, let's say we're standing over here and we're looking this way at the object. We're looking this way, the direction of this arrow. And we're looking at this rectangle here. Well, that rectangle, all that is, if we look at it from this side, looking this way, it's a circle. Now, I know that's not a very good circle, but it's a circle. So let's think about it. We want the volume of this thing, right? Well, how do you find the volume? Well, remember, it's what? It's the radius, right? The radius times pi. So the area of the circle times the thickness. All right, that's the volume. This is basically a cylinder. That's all it is. It's just not a very tall cylinder. Okay, so the thickness of this thing is what? Delta x. We'll call it delta x, since this distance here, this thickness here, is going along the x-axis. We'll call it delta x. If the rectangle is going this way along the y-axis, we can call it delta y. But right now, let's just, we're on the x-axis, so this is delta x. So what would be the area of this circle? Or the area of the circle is what? Pi r squared. Pi times the radius squared. All right. Well, we've got this. Okay, so we need the radius. So keep in mind this line extends on out like this. Okay, so you can see there's your radius from here to here. That's the radius of that circle. Well, what's that distance from here to here? Well, we go from here to this y value here. You see that? To some y value. That's the radius. Well, we need to get that in terms of x. Well, we could say this function here is y equals r, big R of x. So the radius would be what? Big R of x. Okay, that's the distance from here to here. That's this y value here. Okay, well, how do we get that? Well, it's whatever the y value of this function is. Okay, that's the distance from here to here. And then what do? We multiply it times pi, and we square it, all right? So I squared the radius, multiplied it times pi, and then to get the volume, okay, so this is the area, then to get the volume, I multiply it times the thickness. Well, that's where the disk method comes in. So the disk method, the volume would equal A to B times the radius squared times the thickness, dx, and times pi. That's all it is. It's pi r squared times the thickness. See, because the area, the area of a circle is pi r squared. Okay, and so that's the area of the circle, and then when we multiply it times the thickness, that gives us the volume of this thing. And then we're going to integrate it from A to B, and that will sum up those volumes there. Okay, so this is your disk method. All right. So now let's come over here, and I'm gonna just come over here, and I'm gonna write down V equals pi A to B R of X squared dx. That's the disk method. Okay, and you're gonna see how this washer method relates to this disk method. They're no different. Okay, so with this problem, we can go ahead and put our y-axis in there, extend that. We're revolving about this axis here. So if I look at this, okay, let's say I have a function here and a function here. We'll call this function big R of X, and we'll call this little function little r of X. All right, and if I'm going from A to B, and let's say I want to revolve this about the x-axis. Okay, so let's draw in our rectangle just like we did when we looked at the disk method. Okay, so let's draw that in. Well, now this time, look, if we're standing here, okay, and we're looking this way, then what I'm looking at here is something like this. All right, and I know those circles don't look good. Okay, but if you remember what we did with the disk method, we had to find, well, I know I erased it, but what did we have to do? Remember, we had the circle, that was big R of X, the radius. We had to find the area of that circle and multiply it times the thickness to get the volume. Okay, so now if we come here, well, it's the same thing. We've got to get the area of this thing and multiply it times the thickness. All right, so the area that I'm looking for is actually, let me just go ahead and kind of put that in there. See, this right here is the area that I'm looking for. All right, so if I'm looking for that area, well, I need the radius out to the big circle. That's R of X. See, that's our function there. That's the radius is from here to this end. And then I need the radius of this circle, which that would be little r of X. See, that's from here to this end of the rectangle. All right. So to find this area, I need what? I need the area of the larger circle minus the area of the smaller circle, and that will leave me with this area right here. And that's exactly what we have here with the washer method. Okay? So I've got what? The radius of the larger circle squared times pi. Okay? So that's this radius squared times pi. That gives me the area of this larger circle minus, look, the radius of the smaller circle. Whoop. Let me fix that formula. Okay. So minus, and then I've got the radius of the smaller circle. You see that? Squared times pi. See, I can distribute the pi to each one. And so that's all this is. It's the area of the larger circle minus the area of the smaller circle. It's just the pi is factored out. Okay? And then we take this area here and multiply it times the thickness, and that's going to give me the volume of this thing. And then I integrate it from A to B, and that's going to sum up those volumes and give me the volume of the entire figure. All right. Now, what I want to talk about is drawing these things. So if we come back up here to the disk method, okay, so let's look at this. You notice I mirrored this, I revolved this about the x-axis here. But look, you see what I'm doing here? I'm erasing the bottom half. I don't need it, okay? So if you want to draw these things, yeah, you can draw it and revolve it like I did, okay? Let's come up here and label this delta x. But look, remember, all we were concerned about was this distance from here to here, that radius. That's all I cared about. So when you're drawing these things, just draw the top half of it, okay? Don't draw the whole thing. And I'll point this out more when we're working the examples, okay? It just makes it easier to see, I think, because, I mean, you know, look, if this comes down like this, and you've got this, you know, and you draw this in, yeah, I mean, that's what it looks like. But we're not even using this bottom half. All we're doing is looking from here to here. We don't need this down here, okay? And then look, the same thing here. If I'm drawing this thing, you see how I revolve this about the x-axis? Well, all I was concerned about was what? The distance from here to here, and the distance from here to here. I wasn't even concerned with this part down here. And that's why I just draw the top half, put the rectangle in. I know it's revolved down here about the axis like this, but look, all I need is this large radius and this smaller radius. All right. And now let's go back over here to this disk method here. I mean, this disk method is like the washer method. Look, if we go back over here, let me show you this. Now I know this might be boring to you right now, but I promise you it's gonna help. It's gonna make a difference when you're working the problems. It's gonna make it easier for you to understand. So we had the volume is equal to pi from A to B, and that was big R of x squared minus little r of x squared times dx. All right. So if you wanted to, you could look at all of these problems as washer method. Okay. So let's just take a look at this one. I mean, here's your volume using disk method, but look at this. We know this is delta x, right? Well, look at this. We've got this radius from here to here, that's the big radius. That's big R of x squared. Now, look at this. What's the distance from the line we're rotating it about to the closest end of the rectangle, to this end right here? Well, that's what? That would be little r of x would be what? 0. So see, this would be, this would be 0 squared, so that volume would be pi a to b big R of x squared dx. And you can see that's exactly what you have right there. Okay, so let's go ahead and look at some examples now that we've gotten into this. I know that was kind of long-winded, but I think it's worth it for you to be able to look at it like that. So let's just look at this first example. It says, find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. All right, so to do this, we want to sketch the graph. So we got y equals the square root of x. So I'm going to graph that. Okay, so there's square root of x. And look, this one's nice. It's telling me it's going from 0 to 1. So I'm going to revolve this about the x-axis. All right. Now remember what I told you. You don't need to draw the bottom half. You just need to draw your rectangle in there. Well, since I'm revolving it about the x-axis, my rectangle is going to look like this. Now, an easy thing to remember here is that when you draw your rectangle in, if you're using the disc or the washer method, your rectangle is going to be drawn in perpendicular to your axis. All right. And then the first thing I do is I label the width of the rectangle. So in this case, that width is delta x. All right. So look at this. I need the radius, don't I? I need big R of x. What is that? And then look, and we could also go ahead and write in little r. You know, if we look at the, look at the washer method. Okay. Look at the washer method. The washer method's going to work on all of them. The disc method, it's not gonna work when you have stuff like this. You have the little gap there, and it makes a washer like that. So let's just look at this. All right. So, well, I need this distance from here to here. That's big R of x. Well, I know already little r is 0, right? Okay, because that distance is just 0 from the line we're rotating it about to this end of the rectangle. Well, now I need this height here. I need the distance from here to here. Well, that's what? That's y. All right. Now, another thing I want to point out, it's important to go ahead and label the thickness of your rectangle. Go ahead and label that, because what that does is that tells us, okay, r needs to be in terms of this variable, this delta x. If the thickness was delta y, if I had to draw my rectangle the other way, then my r would need to be in terms of y, because I would be integrating with respect to y. And I've got some examples where I'm gonna where we'll revolve it about the y-axis, and we're actually going to revolve some about lines other than the x and y-axis. So try to watch all the examples. I've got quite a few. All right. So what's this distance from here to here? Well, that's y. Well, what is y? What is that height there? That y? Well, it's what? Square root of x. You see it right there. So that's square root of x. And so now I've got my volume is what? Pi from 0 to 1 of big R of x squared So that's square root of x squared. And then we subtract off little r of x. Well, that's 0. So that's just going to be 0. And so then we can say times dx. And see, really all this one was disk method. Okay, but we did implement the washer method by saying, okay, little r is 0. We didn't need it in this problem, but I'm just showing you that you can show that. And so now we've got pi from 0 to 1 of x dx. So this is going to be what? Pi times 1/2 x squared from 0 to 1. And so that's going to be pi over 2. And then that's going to be 1 squared minus 0 squared, which is just pi over 2. Okay. All right, so let's look at the next example. All right, so the second example here, it says find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. All right, so let's go ahead and draw our picture. All right, so we know that the graph of y equals x cubed looks like this, okay? But see, since it's bounded by, I'm sorry, that was the wrong one. Since it's bounded by x equals 0 and y equals 8, okay, we're just concerned about this part of it. We don't need the bottom part. So when I draw this, I've got just that part of the graph is all I need. All right, so there's x cubed, and then I've got the line y equals 8. That's just a horizontal line here. This is 8, and then x equals 0, which is just the y-axis. Now I'm revolving it about the y-axis this time. Okay, so let's draw our rectangle in there. And remember what I mentioned in the video earlier is the rectangle is drawn perpendicular to the line you're rotating it about. Okay, so it's drawn perpendicular to the y-axis. All right, and so the thickness is what? The thickness is delta y. All right. So now I know the function that I'm going to integrate needs to be in terms of y. All right. So I need what? I need the large radius and I need the smaller radius. So I know the distance from here to here, that's big R. Now, R has to be in terms of y, so that's going to be R of y. And then the little radius, well, let's just go ahead and write down big R of y. And then the little radius, well, this is the line I'm rotating it around. And so to the closest end of the rectangle, that's 0. So little r of y is 0. So I need to know what big R of y is. All right. So, well, what's this distance from here to here? Well, if I go from here to here, that's how many units? Well, I'm on the x-axis, so I'm going over x units. Well, what's x? Well, we know that y equals x cubed. That's our function that they give us here. So x is equal to the cube root of y, or we could write x is equal to y to the 1/3. And so this is y raised to the 1/3. So we get our area is equal to pi times the integral. All right. Now, what are we integrating from? Now, remember, we're in terms of y, so I'm integrating, my limits are going to be on the y-axis. So I'm going from here, which is 0, up to here, which is 8. And then that's big R squared, so that's y to the 1/3 squared, minus little r squared. Well, little r is just 0, so that's 0 squared, and so I'm going to be just left with this, and then times the thickness, there's my dy. And so this is going to be pi from 0 to 8, y to the 2/3 dy. All right. So now let's integrate this. So that's going to give me pi times y to the, let's see, 5/3, and then I'll multiply by the reciprocal of that, and that's from 0 to 8. And so this is going to be 3 pi over 5 times y to the 5/3 from 0 to 8. And so let's plug this in. That's 3 pi over 5 times 8 to the 5/3 minus 0 to the 5/3. And this is going to be 96 pi over 5. And I'll show you real quick how to refresh your memory on how to do this. 8 to the 5/3 is the same thing as the cube root of 8 raised to the 5th. So the cube root of 8 is 2. That's raised to the 5th, and that gives me 32. Okay. All right, so let's take the next problem. All right, so example, this third example that I have, it says the region R enclosed by the curves y equals x and y equals x squared is rotated about the x-axis. Find the volume of the resulting solid. All right, so let's go ahead and sketch the graph. All right. Let me get my pen ready. All right, so let's draw the picture. And so we have y equals x. Okay, that's the straight line. And we have y equals x squared. All right. Now, I know that these graphs here, they go like this and like, well, and like this, right? But we're only interested in the region that's enclosed by the two graphs, which is just this part. And so that's why I'm only drawing that. Okay. All right. So now let's see, we're revolving about the x-axis. So we need to draw in our rectangle. All right. Now, this right here is where the washer method comes in handy, because we're going to need what? We're going to need big R and we're going to need little r, the big radius and the smaller radius. So remember, the radius, that's from the axis you're rotating it about to the furthest end of the rectangle, and the axis you're rotating it about to the closest end of the rectangle. And then we also need to put our thickness in there. Our thickness, delta x or dx. Okay. So this is big R and this is little r. Now, what variable is the radius going to be in terms of? Well, our thickness is delta x, so these are going to be in terms of x. All right. So let's get the larger radius. Well, that's the distance from here, from the x-axis, to the furthest end of the rectangle. Well, what's that distance? Well, we're going up what? Y units on the y-axis, and we're going up to the line. So what's y? Y is equal to x. So that equals x. And then we need the smaller radius. Okay. So the smaller radius, that's from the x-axis up to this point on the rectangle. Well, we go up what? Y units. Well, in this case, we're going up to the curve, y equals x squared. So we went up y. Well, what's y? Y is x squared. And so there's the smaller radius. And so now my volume is pi times the integral of the larger radius squared minus the smaller radius squared. And then times dx. All right, now I need the limits on my integral. Well, I'm integrating from here to here. Well, I know this is 0, but now I need this value, this x value. Well, how can I do that? Well, if I take the two functions, the x and the x squared, set them equal to each other, I can solve for x. So you can see that's going to be x equals 0 or x equal 1. Factor out of x, solve it. You know how to do that. So that's 0 to 1. And so this is going to be pi times the integral 0 to 1 x squared minus x to the fourth dx. And so now we integrate this. This is going to be 1/3 x, that's going to be pi times 1/3 x cubed minus 1/5 x to the fourth, and that's from 0 to 1. And so now we evaluate. That's going to be pi times, and that's going to be 1/3 times 1 cubed minus 1, and I'm sorry, I got a mistake right here. You see the x to the fourth? That should be x to the fifth times 1/5 x to the fifth minus, and then we do what? Then we plug the 0 in. But you can see if we plug the 0 in, that's just all going to go to 0. So I'll just put a 0 there. And so when I evaluate this, this is going to be what? 2 pi over 15. Okay. All right, so let's take a look at the next problem. We've got 3 more problems to work. This one and 2 more, so just hang in there with me. So find the volume of the solid obtained by rotating the region in example 3 about the line y equals 2. All right, so we're using the functions in the previous example. So we had what? Y, let me get to where I can write. So I got y equals x, and I've got y equals x squared. Now, let's go ahead and sketch the graph. We graphed it earlier in the other part. And now I need to draw my rectangle in, but I need to draw the line that I'm rotating it around first. Well, I'm rotating it about the line y equals 2. So that's, now let's do that how about we do that in a different color. So I'm rotating it about this line, y equals 2. All right, so I'm rotating it about this line. Remember, your rectangle is drawn perpendicular to the line you're rotating it about. Now, the important thing to keep in mind, the radius is measured from the line you're rotating it around. Okay, so I'm rotating it around this line. So I need this distance. I need the distance from the line I'm rotating it around to the furthest point of the rectangle, and from the line I'm rotating it around to the nearest point of the rectangle. So these are the 2 distances I need. So let's go ahead and put our thickness in. That's delta x. So now this radius is big R, and this radius is little r. All right, so, and I know I'm going from 0 to 1. We calculated that in the previous example. So now I need big R, and I need little r. All right, so let's get big R. So I need the distance from here to here. Okay, well, what would that be? Well, what do I know? I know the distance from this line to the x-axis is 2. Okay? From here to here. But I only need, see, from here to here is 2. But I only need the distance from here to here. So I need to subtract off this distance. Well, what's the distance from here to here? Well, that's what? X squared. Okay? And then I need the distance from here to here. Well, once again, I know the distance all the way down to the x-axis. I know that's 2. And then I subtract this off. Well, what's that distance from here to here? Well, if we go up that y distance, well, what's y? Y is x because I'm on this line. All right? So there's big R and little r. So now I can do my volume. So the volume is pi times the integral 0 to 1 of big R squared minus little r squared, and then times the thickness. All right, so that's going to give me pi from 0 to 1. I'll need to multiply all of these out. Let's come down here and do that. 2 minus x squared squared is going to be 4 minus 4x squared plus x to the 4th. Okay, so that's 4 minus 4x squared plus x to the 4th minus, and then I FOIL this out, 2 minus x, that's going to be 4 minus 4x plus x squared. And so that's 4 minus 4x plus x squared, and then times the thickness dx. All right. So now what we need to do is we need to distribute the minus. I'm going to come down here and do it so I don't have to do an extra step in here. But that's going to be 4 minus 4x squared plus x to the 4th. I just wrote this down. And then distribute the minus. Minus 4 plus 4x minus x squared. And so that's going to give me x to the 4th. Let's see. Minus 5x squared. And then, let's see, so the squares are out, and then plus 4x, and then the 4's cancel out. And so this is going to give me pi 0 to 1, x to the 4th, minus 5x squared, plus 4x, and then times the thickness dx. Okay, so if you want to, you can come down, and do that little algebra down there, combining the like terms and all that stuff. Well, now let's integrate this thing. So I'm going to get pi times, and that's going to be 1/5 x to the 5th minus 5/3 x cubed plus 2x squared, and that's from 0 to 1. And so this is going to be pi times, that's going to be 1/5 times 1 to the 5th minus 5/3 times 1 cubed plus 2 times 1 squared, and then minus, and then I plug the 0 in, and when I plug the 0 in, that's just going to give me a 0. And then once we do the arithmetic here, that gives me 8 pi over 15. And there's your answer. All right. All right. So let's go ahead and take a look at the next one. We're almost done. So let's see what we get here. Find the volume of the solid obtained by rotating the region in example 3 about the line x equal -1. All right. So once again, we're using the same functions that we did in the previous example. So I've got y equals x, and I've got y equals x squared. All right, so let's sketch the graph real quick. So I'm here and then here. Now, we need to draw a rectangle in, but remember, before you do that, draw the line you're rotating it around. We're not rotating it about an axis, but a line. And so I'm rotating it about the line. Let's draw that in a different color. About this line here. This is x equal -1. This is the line I'm rotating it about. All right. So this time, my rectangle is going to look like this. And now remember, the radius, we need the big radius and the small radius. Okay. And that's measured. The big radius is measured from the line we're rotating it around to the furthest point on the rectangle. And from the line we're rotating it around to the closest point on the rectangle, that's little r. So this is big R, this is little r. The thickness of our rectangle is delta y. So we know that big R and little r is going to be in terms of y. All right. Now, let's get the big radius and let's get the smaller radius. All right, so the larger radius, well, let's see. I know from here, let's see. From here to here, okay, from the y-axis to this point, I'm going over what? X units, right? Well, what's X? Well, I've got to get it in terms of Y. Well, I'm going to the curve y equals x squared. So if I have y equals x squared, then I know x is equal to the square root of y. Okay? So from here to here is the square root of y, and then I have to do what? I have to go one more unit. So it's the square root of y plus 1. Okay, that's the large radius. Now the smaller radius, look, I'm going over from here to here. I'm going over x units because I'm moving on the x-axis. Well, I've got to have it in terms of y. Well, since I'm just going to the line, well, I know x is equal to y. And so this is equal to y. And then I've got to go over another unit to get to the line I'm rotating it about. All right. And then I've got to integrate from here to here. All right. So this is 0. Well, we know this is 1, right? That's 1. Well, if I plug the 1 into here and plug the 1 into here, I get y is 1 also. Okay, get the same thing. So now let's go ahead and set up our integral. So I've got the volume is equal to pi times the integral, and I'm going from 0 to 1, and that's going to be big R squared minus little r squared times the thickness. And so this is going to be pi times 0 to 1. Now, once again, we can come down here and we can multiply this out. Well, that's going to be what? Y plus 2 square root of y plus 1. So that's y plus 2. Now, instead of writing square root of y, I'm going to go ahead and rewrite that as y to the 1/2. We're going to have to integrate it. And then plus 1. And that's minus. And then I've got y plus 1 squared. I'm going to square that. So that's going to be y squared plus 2y plus 1. So y squared plus 2y plus 1. And then times the thickness. All right. So let's see what we get here. So now I've got equals pi from 0 to 1. Now, I'm not going to go through and distribute this and show all my work on that. I did that on the last problem. You should be able to do that. So what I would get if I distribute the negative and then combine like terms, I would get negative y squared minus y plus 2y to the 1/2 times dy. And then I'll integrate this. That's going to be pi times, that's going to be negative 1/3 y cubed minus 1/2 y squared plus, that's going to be 2 times, that's going to be y to the 3/2 times the reciprocal, which would be 2/3. Okay, and so then if we multiply the 2/3 and the 2, that would give me 4/3, and that's from 0 to 1. And so this is going to be pi times negative 1/3 times 1 cubed minus 1/2 times 1 squared plus 4/3 times 1 to the 3/2 minus, and then when I plug the 0 in, I'll actually get 0, and then I plug all that into my calculator, or do it out by hand. Equals pi over 2. All right, so now, good news here, we've gotten to our last problem. All right, so let's see what we've got here. All right, so first, let's go ahead and sketch the graph. So find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, and x equal 1 about the y-axis. So if I graph this, so I'm bounded by y equals 0, and I'm bounded by x equal 1. Okay, so I'm looking at the graph. There's the parabola. There's the line. There's the line x equal 1. So this is x equal 1. This is the line y equals x squared plus 1. And I want to revolve this about the y-axis. Now, this one is a little more complicated. And I'm going to use the washer method here, but I'll have another video out on the shell method, and we'll do this exact problem with the shell method, and you'll see the shell method is actually easier than the washer method on this problem. All right. So if you notice here, if I draw my rectangle in here, all right, so let's just say I draw my rectangle here. Okay, you can see little r is 0. Big R would be what? 1. Well, look at this one. What if I draw the rectangle here? Then all of a sudden little r is not 0 anymore. See, little r changes. Okay, now big R stays the same, but little r changes. So what I have to do is I actually need to split this thing up into 2 regions. So I've got this one and I've got this one. So I'm going to actually have 2 integrals. I'm going to have to do this volume and I'm going to have to do this volume. All right, so let's work on the top half first. All right, so I need, well, let's go ahead and put our thickness. That's delta y, delta y. Now I need big R. All right, so big R, now what is that going to be in terms of, x or y? Well, the thickness of my rectangle is delta y, so this is going to be big R of y. And then I need the smaller radius, that's going to be little r of y. All right, so for the top figure, we'll put top, I've got big R. Well, what's the distance from here to here? Well, that's easy. That's 1. What's little r? Well, that's the distance from here to here. Well, I'm going out how many units? Well, I'm going along the x-axis. Well, so I'm going over x units, but what's x? I need it in terms of y. Well, that's this, right? That's this curve, x squared plus y. So I've got y equals x squared plus 1. So x squared is equal to y minus 1. So x is the square root of y minus 1. So that's little r, square root of y minus 1. All right. Now, for the bottom part of the figure, because we had to break it up into 2, let's do the bottom. Well, I need big R and I need little r. Well, what's the distance from here to here? Well, that's 1. What's the distance from here to the closest point? Well, that's 0. So that one was easy enough. All right. So now let's set up our integral. All right, so let's do this top part first. So I've got volume is going to be pi times the integral, and that's going to be big R, which is 1, so 1 squared, minus little r squared. So that's the square root of y minus 1 squared, and then that's times dy. All right, so the next thing I need is I need the limits for my integral, okay? Well, I'm going to integrate this section from here, which I know this is 1, okay? That's, see, the graph of x squared starts here, and then I just moved it up 1 unit because of the plus 1 there. But then I need this y value here. Well, if I wanted to, well, I can set, well, remember, we got what? X is equal to the square root of y minus 1, and here I've got x equal 1. That's this line and this curve. Well, if I do square root of y minus 1 equals 1, square both sides, so I get y equals 2. So I'm integrating this one from 1 to 2. All right. Now, for the bottom part, this is going to be plus pi times the integral. Now on this one's easy. It's just this little square here. I'm going from 0 to 1. Now it's the big radius minus the smaller radius, and then times dy. All right, so I'm going to get pi times the integral 1 to 2. That's going to be 1 minus y minus 1. See, if I square the square root, it just gets rid of it. And that's times dy plus pi times the integral 0 to 1. And that's just going to be 1 squared. So that's just 1 dy. All right, so we've got pi times the integral 1 to 2. Well, if I distribute the minus, that becomes a plus 1. And so, so the 1 plus 1, that's going to be 2. So I get 2 minus y. dy plus pi times 0 to 1 dy. All right, so let's integrate this. So I get pi times, that's going to be 2x minus 1/2, I'm sorry, not 2x. How about 2y times 1/2 y squared from 1 to 2 plus, this is going to be pi times y from 0 to 1. And so this is going to be pi times 2 times 2 minus 1/2 times 2 squared minus 2 times 1 minus 1/2 times 1 squared. Let's see. I think I got all my parentheses in there, right? So then plus pi times 1 minus 0. And then if we punch all that into our calculator or do it out by hand, whichever way you do it, you're going to get 3 pi over 2. And this is your answer. So hopefully you hung around for the whole video. I know it's a long one, but hopefully you understand it now. So check out my other videos. Give me a like, share, and subscribe, and thanks for watching.